Hi, so Flipdots. Everybody loves a Flipdot. There's been quite a few projects online with these things. I've recently started sort of taking a look at these. We've got a potential upcoming project to repurpose these displays, which are originally I think intended for the front of buses, to produce sort of a large display with sort of fairly high update rates, but also XY stacked. Because the problem with these ones is the drivers are on the top and bottom, so you can't sort of stack them in two directions. And I sort of started looking into this sort of briefly. I had a sort of rough idea, okay, these flip dots, they're just electromagnets, you just apply different polarities and they change state. Actually, it turned out to be quite a lot more subtle than that. I actually got to the point of sort of doing sort of prototype driver boards for these. I'll go on to driving methods later, but when I sort of started playing with this, I realised that, the actual driving and these things are actually quite a lot less obvious and more subtle than I first thought. So I thought I'd sort of take a sort of deep dive into how they actually work, and then start looking at drive waveforms and what effect the different drive waveforms have on their performance, so that I can actually look at the most effective, and particularly for this installation, the cheapest way of driving them. Now, the first thing that made me realise that these were just a little bit more subtle than I'd originally imagined was the fact they are actually non-volatile. Playing around, I noticed that once flipped in a particular state, they will actually stay in that state, and actually the retention of that state, even if they're subsequently disturbed. So if we take a sort of close look at the structure of these, we can see we've got these two coils, and there's like a link, this horizontal bar. So this is effectively forming like a U-shaped magnet, and there's two poles at the top, and the dot will either rest on one of them or the other one, depending on its state. And so we can just flip that state by applying a short pulse. Let's flip it one way or the other way. So what's actually happening here is that pulse is actually magnetising this magnet assembly. Now, I'm not 100% sure whether the field is being stored primarily by this horizontal link or by these vertical things, or a combination of the two. It doesn't really matter. But so basically what happens is that these will form effectively a permanent magnet. After the pulse has gone away, it will either be magnetised one way or the other, and depending on which way, that's the way that it will hold the disc. And obviously the pulse will also give it a certain amount of sort of momentum to actually flip it. And one thing in particular I wanted to look at is how the pulse characteristics affect the actual speed of flipping. When you change the pulse characteristics, there's very obvious, you can hear an acoustic change, and they get louder, much more sort of clicky. But I wanted to actually do some real measurements to see what that does in terms of the actual transition speed, so we can look at how to optimise the drive on them, particularly to get high updates of a large number of them. Taking a very close look at the dots themselves, they're made up of three layers. Obviously there's the colour layer on the top, then in the middle there's a clear plastic layer with these little pips either side, and these what provide the pivot. These go into sort of the plastic holes in the frame. Then the other side we've got a layer of this magnetic material. And if we actually look at the magnetic pattern using this magnetic field film viewer stuff, we can actually see the magnetisation here. And if we look at the centre, if I just hold the tweezers at the centre, we can actually see that that's in a centre line between the two poles. Obviously that's where the poles hit in one position, and that's the gap that allows it to rotate. So even this has been obviously selectively magnetised just in that particular zone. So when I was looking at these a bit more, I just noticed that there's also another magnet here, and I was wondering, well, what on earth is going on here? So I thought I'd sort of pretty much figured out how it all worked, but no, there's something else going on as well. So what I've got here, we've got two dots. This one here has got that magnet removed, and this one's got it present. And you can see without the magnet, it will just about flip, but it's very, very weak. It's just not really, it'll go one way but not the other. If I sort of crank up the pulse width, you can see it's moving, but it's a lot slower. So clearly, this dot's a lot less efficient. So I was sort of a bit confused by this, and then I sort of just figured out what was going on. We used the eye prober to actually look at the polarity of this magnet relative to the disc. What's actually happening is that the top pole of this magnet is the same as the pole on the black side here, which means that this side gets attracted to it. And if I just take another magnet and hold it from the top to get the get the similar effect. This is a much more powerful magnet, so this works from a longer distance, but having the magnet in front is, yeah, it's basically equivalent to having it underneath. And obviously you can see when I place that magnet, it then just works fine. And obviously it's polarity sensitive. If I put it the other way around, it doesn't work. So what happens is when it gets the initial sort of kick off to start moving, it starts moving, and then this edge starts being attracted towards that magnet, and obviously it gets very close. It'll accelerate towards it, and then by the time it's hit there, it's got enough momentum to actually carry on moving, and then come within the influence of the other side of the magnet that's causing the motion. So basically, having that magnet is just giving a quite significant boost to the efficiency. So it doesn't need as much energy to get it kicked off. It just needs enough energy to get to kick it off of its initial position, to get it within the influence of that magnet, and then the acceleration does the rest. And also, I think the fact that this is also that these are asymmetrical helps. In this position, the dot is almost sort of flat, facing forward, obviously to maximise the contrast, because the tops of the two poles of the electromagnet are slightly different. When it's in this position, is actually at more of an angle this way. So I think that asymmetry probably also helps with that fixed magnet, so it doesn't go quite as far round as it does on the other way around. So the magnet is sort of attracting it to here, but it hasn't actually got to go all the way to the other magnet. It's actually stopping part way before. But that's a very interesting, very subtle little detail that I only just sort of noticed. Looking through a couple of patents, it's mentioned, there's a Korean patent that mentions it, but it's not that clear how, exactly how that works. It's a little bit too vague to explain why it's actually there. But so it's very interesting little additional detail that I'd certainly never realised. Another subtlety that I noticed in one of the patents, the 2000 US patent, is that the electromagnets they're a steel bar, but they actually have quite a thick copper plating on them. Apparently it says this is to reduce the effective eddy currents, which seems a little bit odd, because I'd have thought that would actually increase it. So I wonder if maybe that's just to provide some sort of magnetic damping type effect, because obviously the changing magnetic field will introduce eddy currents into the metal. This sort of copper looks like it's there to prevent that, but it's not clear exactly how that helps. I can't really be bothered to unwind one of these, strip the copper off and then rewind it just to see what difference it makes. But so it's an interesting little detail. I've scraped some off here, you can just about see the copper colour there. But so another very subtle thing that you probably wouldn't guess just looking at these things. So I want to investigate all the driver characteristics. So what I've set up here is a number of driver channels, basically outputting a continuous flip signal, and I've got a piece of reflective tape on one of them with an opto sensor, so I can actually detect when it's at its final position. I'm also using the AIM TTI eye prober to measure the actual magnetic field. I've taken the dots off of these ones so that the measurement isn't affected by the dot, it's just looking at what the electromagnet's doing. Okay, so what we're looking at here is we've got the ingoing pulse to the driver, the magnetic field, the current that's going into the coil, and then the motion. So where this rising edge is when it's going to its final position. Obviously one thing you can see is a little bit of a bounce. When it hits the end, it's sort of hitting the end, bouncing back. This rising edge is sort of the important thing for the actual visible position. We've got a few measurements here. We've got the pulse width here, the delay between the start of the pulse and the rising edge of here. The rise time of this, which is probably not particularly significant, will give some indication of the speed that it's at when it hits that final part and the peak current. So if we just start off just by looking at the current, what you can see is the magnetic field goes up to a certain point but then levels off. So this is going to be where that magnet basically reaches saturation, and that's obviously enough to flip the dot, because that's if we look at the overall scale, this is while it's in motion, and the pulse is actually very short compared to that, which is something was a bit surprising when I started looking into this in detail. So let's just start off looking at what happens for very short pulses. So we're going to start with this now 50 microseconds. As you can see, the field isn't really doing anything, the dot's not flipping, and I'll gradually increase the pulse width. You can see that the field's increasing, and when the dot's just about starting to move, up to this 200 microseconds, 300. So at 300 we're getting a sort of fairly decisive flip from the dot. As we go up a bit more, we can see that the residual field is increasing a little bit, but not much. So go up to sort of 500. Again, the residual field is now pretty much levelled off, so lengthening that pulse isn't really doing anything for that field. We see the current is still increasing throughout the pulse due to the inductance of the coil, and the magnetic field is still increasing. And then once we get near about a millisecond, everything's pretty much flattening off. The current's levelling off about 500 milliamps. That's due to just the series resistance of the coil, so the effect of the inductance is now not great. Again, as we increase it further, nothing at all is happening on the residual magnetic field. We are getting a higher initial field that's maybe kicking the dot out off a little bit quicker. But yeah, as we go much above that, it's not really making much difference at this end of things. So let's see what's happening now to the actual time it takes to flip. So we're now back down to 500 microsecond pulse, and we're getting around 68 to 69 milliseconds between the pulse and the dot arriving in its final position, ignoring any bounce. And as we increase this sort of fairly significantly, we can see that we're up to we're up to 2 milliseconds now, and it's reducing a little bit, 64 milliseconds. Double that, we're now 4 milliseconds down to 61, so we seem to be getting into sort of diminishing returns already. One thing is noticeable, it is getting sort of quite significantly louder. We're getting like a sort of sharper tap tone. This is now at 5 milliseconds. We're down to 60 milliseconds, so if I now just double that to 10, again we've got a small difference. It's only like 10% improvement for doubling the pulse length, and obviously we're doubling the amount of power we're putting it in as well. And if I go to just something ridiculous like a factor of 10 improvement, so that's now 100 milliseconds, we're only down to 45. It only takes us down to 45 milliseconds, so there's not much we can do to improve that flip speed. But we are burning a lot of current now. Perhaps what we could do is maybe do 2 short pulses. Perhaps if we did like a second pulse around here to sort of try and pull it in a little bit more, I think we could maybe get a little bit. But to be honest, I don't think it's really worth the effort. And I think we're really pretty much stuck with about around the 60 odd millisecond transition time. Now, obviously, this may well vary with different sizes and makes of flip dots. But that means, we only need a fairly small amount of time and current to get pretty much the same result. So literally if I just go from say 500 microseconds, 5 milliseconds, 50 milliseconds, you see it's not even halving the transition time. Yeah, if we are giving it those long pulses, obviously there's 2 potential issues, especially if we start wanting to get high frame rates. Obviously heating will start to be a major issue in the coils, and there may also be some just mechanical issues of these things sort of slamming against the end stops a bit too hard, which might perhaps have some lifetime repercussions. Now, something else to look at is supply voltage. All these tests so far have been at 12 volts nominal. If we sort of reduce the supply again, we're going to get to the point where we're not generating enough magnetic field. That's down to sort of 7 volts. And this is with a 500 microsecond pulse, down to 6. It's starting to get it's now just pretty much died. So 6 volts with 500 microseconds just about works. Timing wise, we're at 86 milliseconds, so between 6 and 12 volts we're going from 86 milliseconds to like 70 milliseconds, so it does make a bit of difference. And obviously if we increase the voltage, we will get a higher rate of rise of both the field and the current. So if we go up to 17, 18, 19, 20, obviously this levelling out is starting to happen earlier as the inductor saturates. And obviously that also means if we wanted to have a narrower pulse, for example, if we had a large number that we wanted to shoot the pulses out quickly, then we should be able to get away with a narrower pulse. So let's try that. So if we go up to I'll go up to 20 and then knock the pulse length down. So this is 100 microseconds now, so that's just about flipping, but I don't think we're really getting enough field. Let me just adjust this field scale a bit. So again, if we go up in pulse length, our residual field is increasing slightly, so we're not quite at where we want to be in terms of the key field to keep it. That's about 200 microseconds, so sort of 200 microseconds at 20 volts. You know, we've got a slightly shorter pulse, so you know, if we were going for maximum number of pulses in a given time, then higher voltage, shorter pulse might be beneficial. But obviously you need to bear in mind that, you know, doubling the supply voltage quadruples the power dissipation in the coil. So that's probably not a huge issue, because you know, you're not going to be typically operating the same dots very quickly. It's going to be you're going to be trying to flip lots and lots of dots at a fairly high rate, but individual dots you're probably not going to. So it's probably more going to be an issue with power dissipation in the driver rather than the dots themselves. These ones, the resistance is about 18 ohms. I'm sure there are probably different flavours of these with different resistances. Let's just have a quick look just to see if we get any major sort of improvements on flip time at a high voltage. 12 volts, we've got 70 milliseconds. 20 volts down to 67. 24 volts, 66. It's not really a huge benefit. We'll try with a slightly wider pulse, up to 5 milliseconds. So we're down to about 60 milliseconds at 12 volts. 15 volts, 61. 20 volts, 60. 24 volts, sort of 59. So that's not really giving us any major benefit in terms of, you know, flip speed, and obviously we're going to be dissipating a bit more power. So it looks like pretty much the only benefit for going a high voltage is if you need to keep the pulses really short. If you want to issue lots and lots of pulses, there might be some benefit for using high voltage, because you could then issue more pulses within the nominal flip time. And obviously if for some reason you needed to work at low voltage, so if you want to be down at 9 volts, then you might want to widen the pulses up a little bit. Let's take a look at this in slow motion. The LED at the bottom shows when the pulse starts. This is the 500 microsecond pulse. The length of the LED isn't representative, by the way, that's not the scale. So you can see it's accelerating off towards that centre magnet, and then now it's going at a relatively constant speed until it hits the final end stop, and then we just see a bit of a bounce going on. And now the same thing with the 5 millisecond pulse. Again, we've probably got some sort of bit faster acceleration, but then after that it's pretty much the same. Let's look at those side by side. On the left we've got the 5 millisecond, so you can see it kicks off fairly quickly, but I think yeah, for a factor of 10 pulse length difference, so we're not seeing a huge difference in speed. It's just that initial kick, and the rest of it isn't that different. Let's look at drive methods for these. This is the traditional method where the coils are wired up in a matrix with a couple of diodes. So for example here, if we wanted to activate dot 1, we set the column 1 line low and then apply a high to the row 1 line, which gives you a positive on the right, negative on the left. And if we wanted to set that dot the other way, we would set column 1 high and then pull the row 1 L line low, so we get a pulse in the opposite polarity. Now of course we could also in principle activate more than one row at a time, so we could for example set 1 and 2 by setting column 1 low and then row 1 H and row 2 H both high, but also you need to bear in mind that the current could start stacking up. We're looking at sort of about 400 milliamps or so, so you know, if you do that for more than a few, then your current is going to start getting a little bit high. Now when I started looking at this, before I'd really looked into the pulse lengths, I was working on the assumptions that the pulse lengths were going to be of the order of sort of 10 milliseconds-ish, which I subsequently found to be incorrect. But on that basis I was working on the assumption, well, that's actually going to be quite slow. If we have to do this sequential process at that sort of speed, then the update's going to be quite slow. Now I know that what the actual pulse lengths are, I think I'm going to revisit that, because originally when I was thinking the pulse lengths were going to be quite long, I was looking at, well, to get a decent update speed we'd have to break this matrix down to maybe like a 3x3 or a 4x4 or something, which was actually going to work out more expensive than the other solution I'll talk about in a minute. But so now I know that the pulses are a lot lower. I think something of the order of maybe a 6x6 or a 7x7 might well be pretty viable. I then sort of started looking at driving individual pixels with each, with an individual driver per pixel, so that each pixel could be driven in either direction without any sort of dependencies on the other, so the timing could be just purely down to software and how what order you decided to drive them in. Now the obvious way to do this is to use an H-bridge, where we have sort of 4 switching devices with their transistors on MOSFETs, so we activate a diagonal pair for one direction and the opposite diagonal pair for the other. This starts getting a bit complicated because we need to level shift between our 3.3 or 5 volt logic signal and our 12 volt supply. So that will typically be done by adding an extra device to drive the upper devices. This also suffers from the potential problem that if you get things wrong and accidentally activate both sides of one bridge at one time, that's going to short the power supply and it's going to cause the smoke to come out. And obviously on a large scale thing, if that amp, for example, is perhaps a power up glitch, then you could get into some quite serious problems. There is another approach taken by a couple of people I've seen online where they use a half bridge with a capacitor. That works. It still suffers from the same issue of needing to level shift the upper side of the drive. The other slight concern is it relies on the fact the capacitor maintaining its charge. So if you set the device with a positive pulse, that capacitor needs to stay charged until that dot needs to be flipped back the other way, which in practice probably isn't an issue, but it does mean there is some risk. Periods are long, you might find that it might not always clear successfully, but you could that could be worked around. But that also still suffers from the issue of if you accidentally activate both sides of the bridge at once, again sort of smoke ensues. So this started looking all sort of fairly complicated, but then I had a sort of flash of inspiration. I thought, well, maybe there are some really cheap drivers for things like small DC motors in toys. So I had a look on LCSC and found that not only, yes, there is this chip which looks pretty much ideal, that same chip is available from at least 4 different manufacturers in pin compatible and function compatible format. It costs under 4 cents each in reasonable quantities. And it does, pretty much exactly what we want to do. It contains a full H bridge. Its current rating is typically 100 milliamp continuous, 500 milliamp pulsed, which again is perfect. It avoids the shorting issue in that it's got 2 logic inputs, which again, the logic inputs both handle level shifting, but also make sure you can't turn both sides of the bridge on at once. And it's sort of pretty much an ideal solution. So if we then sort of couple this up with a 74HC595 shift latch just to provide the IOs, we actually end up with a very cheap solution. So if we use a 74HC595 to drive 4 dots and 4 of these chips, that gives us a cost of a little under 6 cents per dot component cost, which is pretty good. One word of warning when looking for HC595s on LCSC, there are some which are designed for LED signage panels which do not have the enable input, and also I believe have open drain output. So just check the data sheet. This is shown in the data sheet, although it's Chinese, you can tell by the pin annotations, but do check because there are some out there which aren't quite what they seem. But even decent ones, we're still talking about about 6 cents each for ones that work as you'd expect. So this is the board that I came up with. This was a bit before investigating all the pulse lengths. We've got HC595 driving 4 dots, and we're using the enable input of the 595 to provide the actual pulse length. This means that we can load all these registers up and then just give a pulse to get the precise length. It also means we can add some hardware protection against coils being turned on for too long. We just put a simple RC filter on that enable line so that whatever happens with the software, it limits the length of that pulse to the maximum we decide is safe. This is basically a prototype really for evaluations. Because these Flipdots are very hard to unsolder without damage, what we're planning on doing is basically soldering this onto the back of the existing PCB. We're going to need to machine the edges off so that we can stack these vertically anyway, so at the same time we'd machine off the column interconnect lines to separate those so that these are effectively floating. The diodes are still there, but that doesn't matter because the way the diodes are orientated, they're not going to pass current in any operating circumstance. Now, we're in the light of the pulse length experiment, I think I may well sort of revisit the idea of splitting this up into small blocks. It might be I need to look at this board to see whether we can actually make use of the existing diodes, or just maybe cut it into effectively smaller matrix sections and drive it that way. So this is basically where I am at the moment. I certainly should have done some more sort of research into the dots before just barreling ahead and making some boards up, but I sort of wanted to get something happening fairly quickly. I'm still not really sure whether this is the right approach or whether we go to some sort of matrix thing. Also, I want to look to see it may well be possible to actually use these driver chips as part of a matrix drive scheme. Also, we need to sort of revisit whether we can look at, whether looking at mounting boards on the back of these, or whether there might be some way of unsoldering these flip dots there. And it certainly wouldn't be feasible to use like traditional desoldering methods, because there's about 8,500 solder joints on each of these boards, and we're looking at quite a significant number of these boards in the final installation, hopefully. But what I'm thinking about is maybe if we can actually make like a custom big desoldering bar that could like melt all of the pins on a whole module, so you literally could put it on the back and then pull a whole module off in one go. That might actually be worth investigating. But say one of the problems is that we've got this fine wire on the coils that's then wrapped around these pins, and there's two things that I've seen happen. One is the wire itself can be damaged, but also the pins can also pull out of the plastic body, and if that happens, that will just rip the wire off at the same time. So that's something that needs a bit more further research and work. The end goal is to make a large display with a fairly decent update rate. Exactly what form that will take is sort of still to be decided, so stay tuned, and hopefully we'll see some progress on this over the next few months.